Okay, so these thermochemical equations are just the equations, balanced equations, but we've included the enthalpy. So because of that, and that the enthalpy is related to the coefficients in the reaction, we should be able to gain some more information about the reaction, relating moles and grams to heat. So how much heat was absorbed when 50 grams of B2O3 was reacted? And this boron oxide probably has a name. I guess we could probably be diboron trioxide would be it. It's unusual, but it might also have a common name. But we start with this. We have to convert to moles if we're going to work with this chemical equation. And if you're given a chemical equation, generally you're going to be using it for something, for a calculation. Where's my calculator? Okay. So boron. Don't use boron that much. Times 2 plus 48. So this is 70 grams of B2O3, and that's 1 mole. Now we have it in terms of moles. I'm going to double check real quick. Oops. Yeah. And then we look at the equation, and it says for every 1 mole of the B2O3, there was 2,035 kilojoules of heat given off. No need to put the plus sign. You can if you want. I usually leave it off. The big thing to remember is that energy is always positive. If you have a sign on energy, that's just telling you which way the energy moved in the system. So you can always add it in later. And they're not asking for, in this case it's positive, so everything works out, but they want the heat that was absorbed. They're not asking for the enthalpy change, which would be positive or negative. Heat is a form of energy, so it's always going to be positive. So we have 50 divided by 70 times 2,035, and this comes up to 1.45 times 10 to the third kilojoules. Do this real quick. Seems reasonable. Now, another thing we can do, and I'll pull down the back down to the reaction in a second here. 1.63 times 10 to the fourth kilojoules of heat was absorbed. How many grams of oxygen was produced? So we can start with the heat this time. And for every 2,035 kilojoules of heat that was absorbed, what do we do in oxygen? 3 moles of oxygen. 3 moles of oxygen was produced, and 1 mole of oxygen is 32 grams of O2. So this is a measured number, so it's 4 significant figures. This is a number taken from the equation, so it has infinite significant figures. This is 3, this is 3, this is 3. So 3 it is. It's unusual to have a measured number and then an exact number, but that's okay. Exact numbers really don't play a part in finding the significant figures because they always have more significant figures than anybody else. So 69. Grams of O2. So I just want to do this real quick again. And that looks like the deal. All right, let's try another guy here. If 789 joules of heat is released, how many grams of B2H6 was reacted? So we have 789 joules that was released. Could certainly put a negative here because the negative will be here, but I always like to just deal with heat as a positive number in the calculations because that's what it is. It's energy, so it's 789 joules is released. That's the negative. We know that it's negative because that's what Q is negative because it says it's released, but we just want to deal with the heat. And so that's joules. Oh, okay, so dang. So we're going to have to convert to kilojoules before we use what we have from the equation. So for every 36 kilojoules of energy that is released, that's 1 mole of B2H6. And then 1 mole of B2H6. And we have 10.8 times 2 plus 6. So this comes up to be 27, we'll leave it as is, 27.6 grams. Do this out again. Okay. Oops. 10.8. Yep. And divide by 36. Yeah, just it's funny. I rarely use anything with boron in it, so it's just throwing me off. I picked this from a. Well, I kind of made the problem up based off of another problem I found, but yeah, that's what's throwing me off. It's just rarely use boron for anything. All right, now the reason I didn't put a negative here again is if I did, then we'd end up with a negative mass. Because, well, since it was released, you could put a negative there. Why? The energy is energy. Negative just says which way it went, into or out of the system. I just deal with the energies as they are. And then let's take a look at this next problem. It kind of illustrates that idea. You have 566 grams of H2, 2 grams of H2, that's 1 mole. They want to know how much heat is produced, and then the 3 moles of H2, and that produces 36 kilojoules of heat. So we do 566 divided by 2, that gives us moles of hydrogen, divided by 3, that's and then multiply by 36. So that gives us 3.40 times 10 to the third kilojoules of heat produced. That's what they're asking for. If you put that as negative, they're saying how much heat is produced. You're saying negative 3.4 times 10 to the third kilojoules of heat is produced. That doesn't make any sense. They just want to know the amount of heat. Now, if they ask for the enthalpy of this reaction, of this process, then you just, delta H is negative 3.4 times 10 to the third. So you have to understand the difference there. And they just ask for the heat, they want that positive heat. They know that it was produced. They know that it was given off. They've stated it in the problem, so they're not asking you to state it again.